All right, so hi everyone and welcome to this session. My name is Joel Koshi and I'm part of the data infrastructure group at LinkedIn. I'm a member of the Kafka team. And before I begin, I want to say, in case you're wondering, I'm the original speaker for this presentation. Neha was unable to be here, so I'm taking over for today. So I'm going to be talking about our real-time data pipeline, some of the motivations behind it, and how we built it out using Apache Kafka. So LinkedIn, like most web companies, derives a lot of value from tracking user activity. And by that, I'm referring to things like page views, who viewed what, when, clicks, ad impressions, and so on. And some of this user activity shows up in one way or the other directly in your own network update stream. And so someone in your network might add a new connection or share a URL, and you ideally want to see these updates in near real time. So this activity stream is a useful user-facing product in and of itself, but it really is much more important than that, because this activity data is an important ingredient in many of our data-driven products. And we want to take that activity data and use it to provide a richer, more relevant experience for our members. And that in turn engages our members more, and that in turn drives more activity data, and we get into this self-feeding cycle of successful refinement. And that principle manifests in products like People You May Know, which is only as engaging or useful as it is relevant. So if you see this page and you see people you don't really know anything about or are not connected to one way or the other, it becomes useless. But if we show relevant suggestions here, that engages you more and might lead you to connect with that person, triggering a connect event, or view their profile, or company pages, triggering profile view and company view events. So a simple page view directly or indirectly follows up in a number of additional page views and a flurry of downstream activities, so calls into backends and so on. And this activity data is crucial. It's very important to be able to track all of this. And activity data is not the only kind of data that you might want to have in a pipeline. The other important data stream that we have is system and application metrics and logs. So this is very important for you to be able to monitor the health trends of your production systems and services over periods of time. And log data, service call information is very important for debugging and useful tools like service call graphs, and identifying bottlenecks in your system and so on. So these are just two kinds of data streams: user activity data and metrics data. There are a few others as well. And there are a bunch of data-driven systems that feed off of these activity streams. And that is a key problem. How do we integrate all these disparate data streams and make it universally accessible, preferably in real time, to all these data-driven systems? And what happens at many companies, and LinkedIn is no exception, is over time we end up with an architecture that looks something like this, where there's a specialized pipeline for each data system. And in this diagram, the sources, the data sources, the different data types are on top, and the various data-driven systems are below. So we have specialized pipelines for each. For instance, a few years ago, our legacy user tracking system was a specialized pipeline, which I'll talk a little bit more about in a few minutes. For logs, for scraping and searching logs, we used Splunk. And I think our operational metrics was based on Xenos. And we also have, and actually still have, the traditional databases and key value stores that Espresso, Voldemort, and Oracle. And then we have our data-driven systems below, some of which are batch-oriented, more offline, Hadoop and the data warehouse, and so on. And then there are production services, some of which are more user-facing, and some of which are more back-end and mid-tier. So it's very important to have the real-time activity feed, the activity feed in real time. For instance, recommendation systems. It can provide more relevant suggestions if it incorporates user activity early on. And likewise, search systems provide more relevant results if the indexed content is as fresh as possible. Security systems needs to track user activity in near real time to detect anomalous patterns and react quickly. So, so being able to access this data in real time is important, and that leads to this order n squared tight coupling between these sources and destinations. And these endpoints need to know how to talk to each other. So it's kind of organizationally unscalable. And to drive home this point a little more clearly, I'll talk a little bit more about our specific pipeline that we had, our specialized pipeline for user activity tracking a few years ago. So the applications would basically post XML blobs of user activity into a central logging service. And these logs would be periodically scraped and are synced over to the offline data center where the ETL process would take place. So there are a couple of drawbacks with this approach. So the first is this central logging service, even though it's central, it didn't really offer real-time data access to this activity feed to other services in the live data center. In fact, as this diagram shows, the only consumer, ultimate consumer, were the offline systems. Second, the data flowing through this system was raw XML, so it's relatively potentially unclean, unsanitized data, and that's where the data warehouse team comes in. So their job is to suck in all of this user activity data, which comes from tons of front ends, and clean it and make it beautiful, transform it, and generate reports and so on. So if the front and the irony is that's not the ideal stage to do cleaning, because they're not necessarily well versed with what the structure and semantics of the source data is. Likewise, the producers, they don't necessarily know what data is amenable for treatment at the ETL stage. And worse, if people make changes to their data, if they add a field, rename, or remove a field, it can break the ETL process. And then there's, of course, fragility. If the schema changes, I just said that. So the other issue is adding a new schema, adding a new data type. So to make sure that data gets ETL, they'd have to go and talk to people further downstream. So the other problem with this approach is it's inherently batch-oriented. So the rsyncs happen periodically, the ETL process happens periodically, so there are multi-hour delays in getting clean data. And finally, the big problem is the only source of clean data in the system is in the offline system, on the offline side. And that's ironic because in a data-centric company like LinkedIn, that clean data is very important to power insight-driven products, and which is part of the reason why we have Hadoop, so we can ship some of that clean data back into production, although the delay factor comes into the picture. So that's a concrete example of a specialized pipeline, and likewise there are a number of other specialized pipelines, each one which has similar limitations. So how do we deal with that? So the idea is very simple, really, and the key idea is to use a central data pipeline and change that architecture into one that looks like this. So there are a number of benefits with this approach. The first is that there's decoupling between the sources and the destination, so there's no longer order n squared endpoints. You only need to know how to talk to this central data pipeline. Second, if this data pipeline is persistent, it allows unified access to all this activity data, and it allows this for a period of time. And finally, I want to point out that even though we have the central data pipeline, we still have had and still have a separate data pipeline for the database updates, and that's Databus, which I won't be going into in this talk. So how do we implement this centralized data pipeline? So at the time, we were using ActiveMQ for our ad hoc messaging purposes, and we thought we could try and use that to implement this data pipeline. I think we tried RabbitMQ as well. So the approach was to basically take these activity feeds and just hook it up to these technologies. And that didn't go too well. And I think the reason for that is largely because it wasn't designed to scale for the volume of data that we had. And especially when you have consumers that have a large backlog of unconsumed data, we found that performance begins to degrade severely. And in other words, persistence is not an ingrained concept in these systems. And we found that it was hard to scale out, so it wasn't as simple as throwing more brokers at the problem. And so that led us to consider an entirely different approach. And what we ended up doing is a very simple concept, is to use a central commit log. And this borrows from the traditional database concept where you have a bunch of updates that you update tables, indexes, and materialized views, and so on. And you do so in a way that is correct even in the presence of failures. So that's the basic commit log concept. So someone else can take these changes read these changes from these logs and apply it elsewhere. So that's what a log is, right? It's an append-only series of records indexed by time. And we thought we could take this concept and analogize it and use it for messaging. So it's a really simple concept. So the sources, the producers, basically append to this log, and the consumers, they just read from this log. And there are a number of benefits that are clearly visible in this diagram. So first, it's append only, and then the consumers read sequentially, so it's a sequential access pattern. Second, it's decoupled, and we talked about that earlier. So producers don't need to know about the consumers, and everyone just talks to this log. Third, because it's persistent and because it's just reading from a file, if a consumer has a large backlog, it's fine. Its performance doesn't necessarily degrade. It just comes back up and resumes from where it left off. And that's important if you consider consumers like a Hadoop ETL process. Your Hadoop cluster might be down for maintenance, or the ETL jobs might run at a low frequency, which is fine. So when it comes back up, it just resumes from where it left off, and performance isn't necessarily impacted. And that's where Apache Kafka comes in. It implements that concept, messaging using logs. So this is a logical view. I'm not going to go into too many implementation details, but conceptually it's very simple, right? So we have the brokers in the middle, in the dotted box, and you can have one or more brokers. And the brokers basically provide these topics, and each topic is divided into a number of partitions. Each partition is that write-ahead log that we saw earlier. So producers, they send messages that are appended to these logs, and consumers just read from those logs. And there are a couple of throughput-enhancing implementation details, the first of which is batching. So instead of sending one message at a time, the producers batch messages. They can send one message at a time, but usually we don't. We batch messages, and that saves a lot and improves throughput considerably. Second, batching is actually on the consumer side as well. Consumers pre-fetch large amounts, chunks of data, and they iterate off of those chunks. So they're not fetching one message at a time. They fetch chunks and iterate messages off those chunks. Second, third, the batching enables compression. So batches of messages at the producer are actually compressed, and that cuts down on network I/O. And finally, we rely heavily on the page cache. Because accesses are inherently sequential and most consumers are at the tail of the log, they tend to hit page cache, so there's very little I/O incurred. So that helps a lot with throughput. And the other thing I want to say is it is a horizontally scalable system. So you can add more producers, you can have more brokers if you need to, and more consumers as well. So in this diagram, for instance, the consumer below consumes 3 partitions. You could have 2 instances or 3 instances to share those partitions. And the guarantees we provide are messages that are successfully published will be available for consumption even in the presence of broker failures. And on the consumption side, we guarantee that messages are delivered at least once, most of the time is exactly once. There are corner cases where you can have duplicates, and that's typically when a consumer fails and comes back up. And the end-to-end latency from the producer to the consumer is less than a second. So at LinkedIn, we have fully deployed Kafka. It drives, it's basically our tracking system. It's the central data pipeline that I talked about earlier. The cluster size is typically 16. We have 28 billion messages a day. Peak rates, the writes and reads, so 460,000 writes messages per second and 2.3 million messages per second read. Now, even though these are messages per second, because we do batching, the request per second is actually a little less. So we'd have to scale that down by a factor. Currently, we're at 700 topics. That's an ever-increasing number. And there are 40 to 50 live services consuming the data. And each of those services may instantiate multiple consumers. And finally, there are many ad hoc consumers. So people might just spawn up a consumer to tail the log to see what's happening. And every production service is actually a producer. And the reason for that is it emits service metrics information. And as a result, there are a very high number of concurrent connections in every data center. So our approximate topology looks something like this. And the big boxes represent data centers. The main reason I want to show this is we have a mirroring feature which allows you to mirror the Kafka clusters across data centers with a few minutes of delay. And that's a pretty powerful concept because it implicitly means your data pipeline can almost seamlessly cut across data center boundaries. And that means, for instance, the Hadoop cluster in the offline data center can access the activity feed from the live data center in almost real time. And more importantly, you can actually push data back to this data pipeline and back to production for services to consume. So that's a very powerful concept because it enables batch-oriented data to be available in a stream-oriented fashion. So a concrete example of that, so we have these recommendation systems that depend on user activity data, which gets into Hadoop, gets some offline computation and enrichment takes place. And our Hadoop jobs before, they would actually pre-compute and pre-build these read-only Voldemort stores and just push them to production. And I guess for various reasons, it was infeasible to have them update read-write stores directly from a different data center. So we actually had to build the entire read-only store and ship it out to production. So now, instead, because we have this pipeline, what these Hadoop jobs do is they incorporate more recent user activity, and they can push this data into the pipeline. And we have a system called Faust, which is currently under development by the Voldemort team. So what it does is it reads this data and incrementally updates the read-write stores. So it's much more efficient. The turnaround time is much quicker. And the key point is that before we were forced to shove data into production. And the push model doesn't work very well because services may not be prepared to handle that sudden burst of incoming data. Now, you just push it onto the pipeline and the service can just read off of the event logs at its own pace, which is very, very important. So the other key idea we have is to preemptively prevent data fragility, that is data breaking in the pipeline because of schema changes, and to ensure that only clean data enters the pipeline in the first place. And the way we do that is by standardizing on Avro in the entire pipeline. So this is an example of one of our tracking events. I don't really know what it is, but I think it illustrates the concept. This is the schema. All events, tracking events at LinkedIn, it goes through a schema review process, which isn't a heavyweight process. It's just to ensure that some best practices are followed, that fields have meaningful names, types are appropriate, and that information that is required for every tracking event is present. So all tracking events, for instance, are required to have an event header. And it enforces some structure, right? And we also have a programmatic compatibility model. So what that means is, let's say you have a schema currently in use in production, and you need to evolve it, add a new field, or modify it in some way. So we prevent people from making arbitrary changes, and that's very important because we don't want to break downstream consumers. And the rules are fairly straightforward. For instance, if you add a field, you provide a default. You can reorder fields. You can add enums, and basic guidelines are provided. And it isn't too restrictive. It might seem restrictive, but it actually is a good idea, especially if you have 50 plus services consuming your data. And producers register these schemas in a centralized repository, and the ID is basically a hash of the canonicalized version of the schema. So and each message contains a reference, that hash. So the producers encode their messages using an Avro encoding, a binary Avro encoding, and consumers, they read the messages, they extract the schema ID, and they can decode the messages back. And finally, third, because of the first two approaches, the ETL becomes very straightforward. It's a much more streamlined process. And when I say order one ETL here, what I'm referring to primarily is human effort. So before, when you wanted your data to end up in Hadoop or the data warehouse, you would have to likely file tickets and explain what your new activity data actually means and provide some custom parsing logic for it, and you have to talk to a bunch of people. But now, because we have standardized on Avro everywhere, as long as the ETL process knows how to read Avro, which it does, we have an Avro input format, sending a new event type is as simple as that. You just send your new event, as long as it's successfully registered. If it flows through the system, it's automatically ETL'd with no manual effort. And our ETL, Hadoop data load, which is called Camus, is open sourced. That's the GitHub link. So it's basically a bunch of mappers that consume from Kafka and write it to the HDFS. And 10 to 15 minutes, that's the ETA from production to the Hadoop clusters. We also use Hive, so analytics teams use Hive for various analysis. Those Hive tables are registered automatically. And because we have the strict compatibility checks in place, we don't need to grandfather in old data if a schema changes, because the old data can just be projected to the new schemas. So finally, how do we know it actually works? And is it possible, better yet, is it possible to measure how well or poorly your system is doing? So for that, we need kind of a metric to gauge, right? And it's a fairly straightforward objective, right? So all messages that are published should ultimately reach the consumers as soon as possible. So what we really want to measure is event loss and also the lag from producers to consumers. So to do that, we actually have an interesting self-verification process. So the way it works is producers, in addition to sending messages to various topics, it also keeps track of how many messages for each topic it has sent in 10-minute windows, right? And every 10 minutes, so it keeps sending out messages to various topics, and every 10 minutes it will send out a special audit event that says, for this 10-minute window, I sent this many messages for this topic. And likewise, for on the Kafka cluster and the offline consumers, Hadoop ETL, they also maintain counts and emit these audit events periodically. And we have a little application that just consumes all these audit events, and we can reconcile the counts across all these tiers. So on this graph, it looks like one line, but there are actually multiple lines. And I'm not sure you can see it very clearly, but there's a dot on the 4 o'clock window, and you can see the event counts on the right side. So it says, in fact, I can't read it, but you can see the counts that the producer sent, the number of events that the Kafka clusters received. There are multiple Kafka clusters here because we do mirroring across these clusters. And then there's the ETL counts. There is a small discrepancy here. And because we have common information in the event headers, which contains information about the service, the server, the time, and so on, we can actually drill down into this and figure out exactly which server in our production environment is causing this discrepancy, and that's very useful. And below, we also have the lag times, and The reason it's fairly high, like 11 minutes, 10 minutes, and so on, is because it's 10-minute time windows. I guess we forgot to subtract that. So the latency is less than what you see on the graph. Now, we do see discrepancies occasionally, and in the past, the main reason for discrepancies is broker failures. And by failures, I mean even upgrades. So for instance, when we need to upgrade our Kafka clusters, we would have to do a rolling bounce, right? So we take down the broker, upgrade its software, bring it back up. In Kafka O8, which was the previous version we used at LinkedIn, there was no producer-side acknowledgement and no replication of partitions. So availability was not a guarantee, right? So if you send your message and so it's a fire and forget model. The producers just send their messages and that's it. If the broker's down, they're lost. And so we have audit discrepancies in that case. So with Kafka O8, which was just released, it brings in intra-cluster replication, which provides high availability and durability. So even if we do a rolling bounce, the producer knows about it, so its produce request will fail, and it can, when it knows about it, it looks up a replica and it sends the messages to the replica. And that's how we facilitate high availability and durability. So the beta release is available on the Apache website. It was released last week. It was rolled out in production last week at LinkedIn. So it's a very big deal for us. It was a very big undertaking. So we want to really thank everyone in the open source community who contributed to the release. So I didn't go into too many technical details of Kafka, but this talk was more on the data pipeline. But we do invite everyone to come to our user group meeting at LinkedIn tonight at 7:30 p.m. I'm going to leave this slide on, so if people are interested in signing up, they can go to the meetup link and RSVP. I believe we have streaming as well, so in case you can't make it and want to watch the presentations, and we have good presentations lined up from companies that use Kafka right now. I think that's all I have, so we do have some time for questions.
Queues. How do you prevent an unauthorized service to pull messages out? And my second question is, are you guys using compile Avro POJOs, or are you using generic items? So if a new schema is published, how does the consumer know there's a new schema and a new field has been added?
Okay, so the first question was security. Right now, we don't really have any secure channels to and from Kafka. So yes, anyone can send and anyone can read. Of course, if the producer can encrypt data if it wants to, but then all the keys and things like that would have to be maintained by the client. And the other thing is, I think encryption will potentially impact throughput because the compression won't be as good. For your second question concerning schemas, we do use generic records mostly. That's how the ETL process works. Because if we depend on specific records, then the ETL process would need to actually know of every new data type that comes in, but we use generic records. Some services at LinkedIn, of course, use specific records because you can convert back and forth.
Hi. I have a question about Kafka Audit. Mm-hmm. I know there were some talks about potentially baking it into Kafka directly, but I don't know if that has been planned for O8 or anything like that.
Yeah, in fact, I think there's a Jira open and there's a patch on that with some code. The problem is the audit trail depends on having information like the timestamp of events. It requires, and at LinkedIn, our event headers include things like service name and the server, which works for us but may not work for other people, right? So it's very Avro specific right now, and we also use this schema repository. So, open sourcing the whole audit trail would entail open sourcing that as well, which we can do. And I'm not sure if that patch contains that, but the problem is it's very specific to our use case, right? It's a general approach to auditing, so it can be implemented in any way you want. The concept is very simple, but unfortunately our audit trail implementation is very specific to our use of Avro and the format of the event header.
Although I remember reading from that ticket that there were potentially ideas about adding timestamps directly into the Kafka message format. And since there are some compatibility changes anyway going to O8, maybe it would have been a good time to add as much compatibility breaking stuff as possible in one shot.
Yeah. I think it is reasonable to do that, but then again, if you add just a timestamp, then you have limited insight into where your discrepancies are coming from. You maybe right. So to have a really useful audit trail, it's important to be able to drill down. I think that was part of the reasoning why we decided not to add it in O8. Yeah.
I see. Thanks.
Yeah. Thank you for the talk. I do have two questions here. The first is, how can you handle the old data? Like if we publish a lot of data, and do we clean the data after 30 days or like the 2 months?
I can't hear. Could you repeat that?
Do you handle the old data or the old archive data?
Oh, okay.
Assuming the data already published more than a couple of days, how can you handle that?
Okay.
That's the first question. And the second question is, do you want to do any kind of optimization for the reader part? Because maybe there are some hotspot data will be quite popular and will have a multiple service want to read. So maybe it will be advantage based on the old access pattern. The system read the pattern first, read data first, put in the memory, and so become like the pre-cache mechanism for the reader side.
Okay, so I can, let me try and answer the first question and let me know if I misunderstood. So I think the first question was on persistence, like dealing with old data.
Yes.
So we, at least at LinkedIn, we configured our clusters for 7-day retention.
Oh,
so after 7 days, messages that were sent 7 days ago effectively fall off. And that works fine because most services are at the tail, and people who have some backlog, they tend to be a few minutes or hours behind. And also because the data is ETL'd into Hadoop and Hive, you get the historic data there. It's always there. So even if the data is not present in Kafka after 7 days, you can grab it from Hive if you need to do some analytics. Is that your first question?
Yes.
Okay. Now the second question was, what if you have topics that are read by multiple people?
Yeah.
Right? That's fine, right? Because consumers are basically reading off of these streams of data, which is reading off of log files, right? So it is intended to, you can have multiple consumers without impacting your performance severely. So so there are consumers reading from multiple topics, right? And the access pattern is sequential. So it's really a matter of scanning through your files. It's having more and more consumers reading from those topics doesn't really affect performance significantly. Also, in the stats that I provided on our read and write rates, you might have noticed that the rate of reads is much higher by a factor of 5 or something. So for every message produced, you have on average 5 consumers reading those same messages.
I see. Okay, thank you.
I have a question on the partitioning. If you're using, I'm assuming the producers use a key to send the messages to each specific partition. Can the consumers also use that same key or choose which partitions they connect to and consume from? And so if it's failover, they're always guaranteed to only read from the same partitions and thus only consume the same type of data.
Yeah, that's a good question. So producers do produce with a key. By default, they use a null key, which means random partitioning. But if you do specify a key, it will be, and you provide a partitioning function, it will be directed to a specific partition. On the consumer side, so we have 2 kinds of consumers, simple consumers and high-level consumers. The high-level consumer is not key aware right now. So what happens is if you have a consumer group with like 10 consumers, it'll take the available partitions and just spread it across those instances. So you'll have to have some custom logic in your consumption side to, if you are responsible for a certain, yeah, I guess that wouldn't work. So right now, because it's not key aware, the high-level consumer, you'd have to basically use a simple consumer to exactly specify which partition you want to consume from.
But if you're using a simple consumer, how do you know which partition contains that range of data?
Yeah, that's a good point. So you'd have to know that in advance. Yeah, you'd have to know what the partition function is. So typically partitions, one example is partitioning by member ID, right? So one range of member IDs goes to one partition, another goes to another. So the consumer knows the range of member IDs, right? And it can, so we have a metadata request so it can look up the available partitions for a given topic. And so you need to know the distribution of keys across those partitions. Without knowing which partition you need to consume from, it's not possible.
I have a question. You kind of touched on, you tried on existing technology like ActiveMQ and Qubit. Can you elaborate a little more on that? Like, what are the reasons you see on the limitations, especially like Qubit, which was proved to be a working technology for message broking?
Mm-hmm. Yeah, I don't think I can elaborate too much. It predates my time, but what I know of it is really scalability and the volume of data we had. And like I mentioned, what we found is when there's a large backlog of unconsumed data, it just starts, performance is impacted severely. And I think part of it is also because many JMS systems, they try and implement a bunch of features that we don't really need. So that could be part of the reason. Any more questions? All right, well, thank you.